Thank you, Thomas, and thank you all for giving me this wonderful birthday singing on Monday. When I was thinking about what to provide you today at this lecture, I thought you might be exhausted. And that's why I decided to, somebody might call it a fairy tale, somebody a dream, I call it a vision. I will go into a vision which I had for a long time, and others in our field too. And therefore, you just can relax, can enjoy the vision, you can believe it, you cannot believe it, it's up to you. But I will try to lead you to how I came to that field and what I'm aiming for in the next 2 decades. And usually I'm thinking in decades. First of all, it was an amazing Congress. I never expected this kind of people of excellence, of exchange. And I think Donna Menrick was right. She said she always taught us for 10 years or 15 years, do not overdo, but over-deliver. And I think in the fields of single organ system and multi-organ systems, the last 4, I'm concentrating on microfluidic systems, the last 4 days have clearly shown that we have a lot of things already delivered, maybe even over-delivered, and we have still a long way to go, but the field is there, you are there, and it works out. That's why I decided to go for something which 4 of us kind of pioneers in the field were inspired already, latest for some of us in 2010. We made it earlier with the idea of finally driving all this field toward a human body on a chip, an entire organism on a chip. And my motto always is, have no limits to your vision, but then test for feasibility. And this kind of, from my point of view, ultimate vision to get into that organismoid level or human on the chip level is really a great vision, but to test it for feasibility will take some time. And I will lead you through some findings. Now, currently, we define organismoids as miniature, mindless, and emotion-free, self-contained physiological in vitro equivalents of an individual's mature human body. So an individual, one person. With that definition, would you believe that this is possible? For those of you who believe it or answer with yes, please raise your hand. Okay, I'm a friend of KPIs, so that is my first question. I will repeat that question at the end of the study. So this is us, and us, we are a mind, a soul, and the body, right? And the body is developing through an ontogenesis, which for humans takes approximately 20 years, which is very different from all other creatures on this earth, and that has probably some reason. And then over decades, a mature adult body stays performing, functioning more or less in homeostasis. And we are endless, so you can describe our body. A 73 kilogram adult person has 10 to the power of 13 to 14 cells. 10 systems include 65 organs and 224 cell types. According to Wikipedia, take other sources, you get other numbers, but we are endless, we are definable, because we are defined. And if you provide 2,500, at least 2,500 kilocalorie after our morning runs, probably more, food, drinks, and at least 750 grams of oxygen to these bodies, they self-sustain. And however, our homeostasis is somehow disrupted by periods of illness and hopefully recovery, right? And that is something in our vision, we need to, which if we can finally model that on the basis of organismoids, I see really another disruptive step of microphysiological systems coming up. Now you know the different levels of biology, and there has been several times here on Congress. Robert Hooke has been cited with his fundamental unit of life being the cell. In reality, I'm quite sure that the fundamental unit of human life and vertebrates and others, whenever we came out of the water with low oxygen, is blood perfused, are the so-called, I called them a long time ago, physiological organoids. So those functional units which are driving each of the organs and are really reflecting the organ functionality. So here in 2007 we described it that nature created this very small but sophisticated biological structures to realize the most prominent functions of organs at a very small level, which is attractive for us as microphysiological system developers, right? And the combination of them finally brings you to the organism level. So that's why we in 2012, we described it, we are aiming to build organismoids on the basis of a downscale factor of the human body, reflecting the functional organoids. And we have decided in our technology a long time ago that we go for a downscale factor of 100,000. So instead of 1 million lobuli in the liver, we have 10. And you need to relate this number of functional units in the liver with a respective number of intestine, skin, lung, alveoli, kidney, and others. And finally, we need, as a community, need to define, if we start to believe in that concept, how many organs need to be put together to have a minimal organismal homeostasis on the chip. And I want to go through that a little bit. It all started, this idea was proposed in 2010 to the European community as a FAMOS project. We called it vascularized multi-organoid systems. This was rejected, but it already included our exposure of like a body on a chip in a mini and a micro format. And on this basis, we already were able to build our, currently we call it Humimic XX and Humimic XY chips. At that time, however, in parallel to that rejected project, we got a smaller grant from in Germany in 2010, and we started the spin-off together with a collaboration with the Technical Universität. Here we had a number of partners which were in, but this smaller project was then concentrated on liver skin due to the resources, the smaller resources we got. But we could use our body on a chip design and reverse design easier combinations of chips for that particular project. And that was something which is still driving us and helps us to make any prototyping on the chip. Okay, let's start. Enjoy yourself and start to be inspired. I first want to go through an historical sketch because I like to read old papers, and I like to give you my learnings around, from that history. In the second part, I want to give you the last 13 years after we have founded this relationship between the Technische Universität Berlin and tissues, and finally a summary and an outlook. The most inspiring reading were the 2,500 pages of William Rouge in German, Der Kampf der Teile der Organismen, the struggle of parts of organisms on the self-regulation of living organisms. Wilhelm Rouge was the first who started to make in vitro culture with neural plate from embryonic chickens for 13 days at that time, but the most attractive findings are how he watched patients. And he clearly defined the different levels, molecules, cells, tissues, and organs, and clearly decided that whenever organs are in struggle, in patients or in healthy bodies, they can hold and confirm long-term homeostasis, and if they don't struggle, these people die. And that is something what he described in that things. So, and he, by the way, started to say, okay, all these levels are following the functions of what we today call form follows function at each level of biology. Genetically encoded self-assembly guides architecture was another learning from these readings, and an active organ crosstalk enables long-term homeostasis. If you don't have an organ function used, you will not have a homeostatic organ functionality over a long time. Now then it took another 45 years until Honor Bridget Fell produced the first bone organoid in vitro. And it took her 27 days using 10 drops of plasma and 10 drops of embryonic extracts as clotted by serum to develop from nearly nothing 6 millimeters still cartilage bone. The early bone, embryonal bone is cartilage. Again, a lot of learnings. At that time, no clean benches, no antibiotics, no synthetic media, no CO2 incubators were invented. But the use of an embryonic extract today, so let's say the grow and embryonal organoid media and plasma, which is the mature body fluid holding the mature body, helped. And we learned, in addition to the fact that an amazing self-assembly capacity is with embryonic tissues, I learned that the microenvironment impacts the development speed, because in reality it takes 3 days in chicken embryos to make this size of bone, and that immunocompetence matters. In that clots, you have complement factors, and and you have in this liquids antibodies, and that probably prevented contamination of this cultures just in watch glasses. Now, in the middle of the last century, particularly after the Second World War, we had an explosion of cell culture and research, and it is I kind of correlate this phase exactly with the phase we had the last 10 years. So the first invention of a murine tumor cell line, establishment of the cell line, the first establishment of a human cell line, and all the media which these guys invented, plus the first separated filter membrane, which is like the today's Transwell, and the patent on polycarbonate invented by Hermann Schnell in Leverkusen were starting a large number of publications and research in conventional static cell cultures of different type, and finally got to high throughput, and that all became also a big industry. And the easy to handle part of that game, easy to handle immortality, let us, from my point of view, had an impact on research directions. So at that time, simplicity of tools, easy to get, disposable tissue cultures, get everybody in quite inspired to say tumor cells are human physiology. If we take tumor cells, we can learn about human physiology, which was wrong, but has created a lot of scientific data. Now, the shortcomings of that standard culture systems were always and are that the human primary tissue density, which is around 10 to the 8 to 10 to the 9 cells per milliliter, cannot be reached in such cultures, nor, consequently, organotypic architecture and functionality. So form in this situation is not able to follow function. And that has been shown in '68 already by McLymetz, who was the first to invent it, that if you take a little bit more than 1.2 millimeter of medium on hepatocytes, they immediately start to differentiate. Now, and that is, I think, the main finding or main understanding we need to draw from that, or at least I drew from that things, is that the oxygen content which is brought to any of the physiological organismoids into the capillary is magnitudes higher than the oxygen level in any 37-degree water solution like our culture medium. We can dissolve only 7 milligram per liter oxygen in that solutions. And by the way, the content of oxygen which is leaving the physiological unit after approximately half a millimeter to 1.5 millimeter of capillary space, the venous blood has still a magnitudes higher oxygen flowing back to the heart and to the lung. This solution, the biological solution to decide to bring oxygen by erythrocytes to the organoids, was the reason why we could step up and run out of the water and some other interesting things. And the important thing I want to highlight here is that this, our biological evolutionary solution with the oxygen, is very critical to oxygen changes and also very stringent with regard to osmolality and pH changes, which has been already yesterday given by Thomas. So if you run out of these ranges in osmolality and pH, we have a significant trouble with the patient. Whilst in our cell culture, like static cell culture compartments, the osmolality varies continuously, and the pH is normally like going back and forth in this range, and depends on feeding intervals, and rarely somebody is monitoring that events. So oxygen shortage, limited nutrient supply, and insufficient waste removal prevent physiological organoid formation for a mature organoid. That was a drawing from here. However, everybody, like researchers, were interested in primary cultures, and they started to use primary cultures using these kind of tools. And therefore, it's not surprising that those which made it to papers or to essays, like you all know the Dexter assay, right, for colony forming of hematopoietic cells, are those ones which don't need too much oxygen in our body, right? So that we have exemptions, and first of all, these are low oxygen tissues and cells are early embryonal tissues. That's why organoids run, stem cells, cartilage, fibroblasts, and a number of subpopulations of immune cells and endothelial cells. Yeah? So the learning here was that hematopoiesis and early fetal organogenesis are partially possible. That was an important learning for me, because then I could understand why these things are really working. Also, I didn't expect that. So I don't go into any in vitro organoid history, because Matthias got a perfect lecture on that. And he highlighted the pros, elements of architecture are there, premature functionality and stem cell niches are there. The cons are lack of blood perfusion, connective tissue bed often is not there, immunocompetence is often lacking here, and we don't have innervation where we need it. Now, with regard to this crucial problem with oxygen supply, in 72, Knatzek invented the hollow fiber. That is the hollow fiber which Thomas just mentioned. And these hollow fibers were just like based on an artificial kidney, a bundle of hollow fibers with an ultrafiltration membrane, and you could perfuse a lot of medium through that, and that allowed really to actively perfuse the extracapillary space of cell cultures, have a lung-like oxygen transfer, and kidney-like waste removal from the tissues. And these systems started to become automated temperature and pH control. So they were able to produce the necessary tissue density. And in Charité, where I was supposed to work, at the beginning of the 90s. In Charité, the Charité formed two groups which were working with hollow fiber bioreactors for any medical or monoclonal antibody needs. One with the immunology, this was my part of the game, and the other one is liver. I give a little bit more later. So since that time, I was able to work with hollow fiber bioreactors, specific ones which had incorporated silicone membranes, and that allowed us to really culture a lot of immunological cultures for a long time, as long as we're talking about non-activated immunological secondary immune organs like lymph nodes or PBMCs or tumor like leukemia cultures over months. We usually stop these cultures after half a year just for economical reasons. As soon as they are activated cultures, it was much shorter, but you could learn a lot. And here you see this hollow fiber and the tissue density which is coming up with them. So with that information, we got along a lot of interest. We had human bone marrow and leukemic bone marrow for a long time, and we learned how to load the bone marrow-based erythrocytes again with oxygen and making them the oxygen transfer entity in that bioreactors. In addition, we started to develop lymph nodes, artificial lymph nodes, and Christoph Giese and his group in one of my other companies in 2004 patented the first lymph node, and we learned from how these white blood cells extravasate from the venal part of the vessels into the lymph node and try to catch these try to check if some of the antigen presenting cells here, the dendritic cells, is fitting with a T cell receptor. And that then brought us to a hollow fiber based concept for a lymph node where you can perfuse the white blood cells and have already a bed of dendritic cells, and you have oxygen as a steep gradient from one part of the lymph node to another at a size of half a cubic centimeter lymphoid tissue. And indeed, you can, as many other microphysiological systems have shown here during the Congress, you can activate these kind of artificial lymph nodes, I would say, but after a while they deteriorate, and the reason is that these organs, single organs which are not used, are going into depression. That is not only true for lymph nodes. If nobody is using the plasma cells and the B lymphocytes and the antibody in the circulation, these single organs start to die. That was a good learning, and we learned that one of the good readouts, but I have seen that in different presentations here also, is always to check for the primary and or secondary follicle formation in that areas, right? If you see the three cell types, the dendritic cells, the T cells, and the B cells interacting and getting into a follicle-like structure, you have the first step. For the immunological part, because I don't want to come back to that, keep in mind that secondary immune organs, like the development of secondary follicles and of germinal centers, are intermediate processes. They grow and they go away, they grow and they grow away dependent on antigen levels, whilst the hard structure of this lymphatic area here, where you have the blood and the arterial blood, they are steady structures which you need to keep in mind if you build lymph nodes. Now the second group was Jörg Gerlach's group, who invented hollow fibers for half a kilogram porcine hepatocyte culture. And he used that as support systems for patients which had a total failure of liver. And he produced bioreactors which had an oxygenation membrane, a bundle of membranes crossing with a plasma infusion for fresh plasma, and a plasma secondary infusion for kidney, like for waste product removal. And that systems worked entirely on the patient's plasma, nothing else, no cell culture, no growth factors, nothing. It was the patient's plasma which kept these 0.6 kilogram person liver cell alive, and then in response these organoids, like these physiological, near to physiological but porcine organoids, kept the patient alive because they interacted with the other organs of that patient. So the learning here was the typical arrangement of primary liver cells, human plasma perfusion, and efficient waste removal and lung-like oxygenation creates an in vitro liver fully replacing its in vivo counterpart. And I don't need more validation than the fact that these patients survived over weeks with that particular livers. And that is a fast track validation, but it is an important part. Now the problem with hollow fiber bioreactors is that they lack biological barriers. These are hardware fibers, and their downscale is limited to 0.5 cubic centimeter in cultures, in single culture space. So they are not an option for microphysiological systems. We collaborated with Heike Merching, today Wallis, who was able to long-term maintain vascularized functional human 3D liver tissues at organoid cell density in so-called vascularized liver systems. So in this case, a cellularized jejunum from animals was used with the entire vasculature. They were fed with endothelial cells again, and in the inner of the jejunum, human hepatocytes will be connected. They grow up to fill the liver sausage finally, and they built the small vascular structures, even of capillaries. And that was again a learning, but again, we learned about arterial and venous flow in that systems and about the background, but the downscale and the of acellularized biomatrix-based culture spaces to organismoid microscale is also impossible. Now, to highlight the problems with oxygen again, or with the functional organoids, living organoids, keep in mind that the liver lobulus has a 500 micrometer stretch between the hepatic portal vein and the hepatic arterial influx of blood and towards the central vein. So only 20 hepatocytes are on that stretch because they are 20 micrometer in size, right? And within that short period, they need to make all the processes we know for hepatocytes. And by the way, they are zonated, so the first hepatocytes are doing other things than the last hepatocyte within that very fast process. And keep in mind that the blood flow is going from outside into the lobulus, whilst the bile always accumulates the other direction to the bicanonically. Let's have a closer look to the liver more on a dynamic basis in that short video, because I want to highlight some other interesting things. So here you see these are, it is always a mix of arterial and venous blood. That's why the PO2 is not so high, but it is still a steep gradient, and that are the bile duct things. And here you see the tissue, and this is the vein here. And you see that within that tissues we have this movement, and we have the zonation of these tissues where the functional, where the cells are doing really different functional job. Also, they are hepatocytes. Not more important, these are the endothelial cells, and they are massaged by the erythrocytes, and they have open spaces, so they are fenestrated ones, so the plasma is massaged into the space disse to the microvilli, and therefore a lot of plasma can be processed in this period. Now, on our chips, we are still, as many others, working with heterologous liver spheroids. You probably have seen that, and try to manage the fluid flow in a way that we at least have the right conditions with regard to oxygen and nutrient exchange, oxygen supply and nutrient exchange. Okay, that was the first part of the game. So that was kind of the historical one, and now we came up with our building the company and this joint Technische Universität company background. I will give you a few data here. Now, we have seen many of the things. The attractive thing for us was that we could reverse design any of our chip backgrounds from the initial body on a chip solution. You have seen that we have a lot of organ models already in place and a lot of combinations. We have benchtop systems and automated systems in place, and we used very different, we can use different cell sources here. I will later highlight how we established our own IPS background, but first of all, our validation procedure here. So we again decided to bring these technologies as fast as possible into laboratories worldwide, because I believe that the device qualification, and the chip qualification is better done within any other laboratory in the world. If we make the right tech transfer to these laboratories, they are using it. If they are using it, new assays appear, new discoveries appear, and if these things are comparable with within laboratories which use the same platform technology, that then allows to gain qualification data on the basis of external power and not internal power. Now, with regard to the IPS cells, we decided very early to build an own small IPS cell bank with the right ethical background and with the right written consents. We used a Caucasian family tree with 3 generations and males and females, and produced 6 banks which have been totally fully characterized and published in the Human Pluripotent Stem Cell Register, and they are available now for working, and we are working on them. We have some workhorses, for example, the 101 here. This is again a male. Yesterday we discussed about males and females, but we have females here too, as you see. And we started to establish one after another many of the tissues which we were working normally with primary cells or with patient cells, in order to make sure that we can produce robustly, can produce organoids of that. And you see that most of them are in the range, the time for that protocols are in the range of 3-4 weeks. An exclusion here is 16 weeks for the skin organoid. I just want to highlight it because this was an amazing PhD student who was ready to make a half-a-year single experiment, right? So if you imagine half-a-year single experiment, but the cool thing with skin organoids, which is well known now, is that after 180 days or 110 days already, here 106 days already, you have a number of structures, sebaceous glands, adipocytes, connected, the sebaceous duct is connected to the hair things we see, hair shafts here. These are lanugo hair shafts. These are hairs which also appear in embryonic on your babies, by the way, at the same week, and then disappear again. But that is interesting to show. That shows that even with low oxygen in the cultures, you in embryonal wise, you can create attractive appendices and biological structures for humans. Now, as you know, our background is based on an on-chip pump. We have a small on-chip pump because we wanted to have the blood to tissue ratio at a reasonable scale, and wanted to have a pulsatile flow which allows us to change the frequency of arterial blood pushing, and a clear understanding about the shear stress and the velocity we are creating. Do we need to help a baby here? I'm a physician, I can help, but I'm not sure. Okay, I'd selected one case which is the most attractive for us because it was the largest step toward human bodies on a chip from our assay background. This is modeling the intestine, liver, kidney, brain, and blood-brain barrier in one chip. Intended context of use was multi-purpose use with focus on ADME profiling, pharmacokinetics, organ-specific toxicity, and BBB permeation of drug candidates. And that was a long program and is still ongoing under Eutox risk, with Risk Hunter and with Hipstar partnerships. And it came from an internal program where we developed a 4-organ chip just on the basis of combining a skin, an intestine, a liver, a skin, and a kidney on a normal first prototype chip here in our in-house between 2013 and 15. And when we used skin biopsies here, liver spheroids here, intestinal barriers from MADEC in this position, and only proximal tubulus cell monolayer, no glomerulus at all, we found out an incredible stability of the system. Also, we overloaded it totally with glucose. We added even glucose to the urine compartment, to the urine circulation, in order to understand how these 4 organs, but we were primarily interested in the ATME axis, how these react to this overload and the combination. And that amazing stability and the ability of the system to bring the glucose down always very strict into into physiological glucose of humans was an exciting finding with a number of other data. You see that even the intestinal part, the matic intestine, started to grow through 300 micrometer with no vasculature, right? In order to feed and to communicate with the others and try to get the glucose in the blood circulation on one level, and we have different other levels in the apical part of the intestine and in the urine, right? So we went to the pharma industry and asked, is that cool? And the feedback of the pharma industry was devastating. They said, okay, first, this is not an ATME axis arrangement. Also, it looks like an ATME axis. You need to have relevant organ flow rates if we want to make calculations. Take a brain instead of a skin. Pharma is not too much interested in skin. Add a glomerulus, this is not a kidney, and make it autologous, otherwise we will have organ rejection. And with that, we were back to our initial design and said, okay, let's just design the next model on the basis of an computational PBPK modeling out of the 4 organs which we had earlier already designed to work with, and make it first without endothelialization and blood-brain barrier, and later with endothelialization and blood-brain barrier. And that was a joint effort in the Eutox program, and luckily we have had here fantastic partners for each of the 4 compartments. These partners had luckily the European production sites, so we got these organs or organoids or tissues from different parts of Europe, and then provided the necessary logistic to get them all in place in our laboratories, run the process here, and make a repeated dose haloperidol and carbamazepine study in order to understand if they are working. So that is a chip. It's by its device. You have this blood circulation background with the intestinal part, the liver, and fresh blood here, the kidney and the brain. And this is circulating, and you have second circulation for urine in our chips. And if you put them together, then with that layered procedure and microscopic access from below, you can get a very good combination. And if we look for the result in that chip, we see that we were able to use this administration, distribution, and metabolism and excretion background, and haloperidol as well as carbamazepine in the different compartments followed the very clear absorption, kinetic, and metabolism and expression profiles of patients, the same for haloperidol. And that was a kind of proof of concept to step toward the next level of that system. We built all these components from a single IPS cell line and tried it again. In this case, we added from the same IPS cell line and BBB endothelial differentiation protocol between the brain and the brain model or the neuronal organoids and the circulation, and again atenolol and carbamazepine being known as low and high blood-brain barrier transfers in a single application after 48 hours came up with really stable concentration in all compartments of the chips, and that was our proof that such chips can work and can provide ATME profiles. And that is the first time that we now have a background where the blood flow is continuously having the same homeostatic concentration of waste products, which is not possible usually during normal life. We need to have IPS-based dossiers for how to make all these tissues. We are doing that with a certain quality control. We finally used our Humimic XY chip already first time for a number of the same approaches, but with 6 or 8 tissues currently. That is all preliminary data, and we learned here for the body on a chip concept that we need efficient on-chip homeostasis to produce a blood on the chip from the bone marrow. We need physiological blood capillaries at each organ level, systemic whole blood circulation, lymphatics and trained cells of the adaptive immunity, organoid innervation, differentiated sex organoids, and methods of inducing human disease. Still sounds like a lot, and I only want to, we will check with the time, go into some of these informations and show you some of that. At this time I need to interrupt shortly, and as an organizer and in interest of other organizers, I want to ask you one question which is not related to my sit back and thinking lecture. Did you learn anything new and surprising for you at the MPS World Summit? If the answer is yes, please stand up. Lena? Sounds good. Please sit down. Okay, let's go into bone marrow. If blood is a necessary part, you need to have bone marrow on a chip. And the bone marrow, we have wonderful presentations, and there are many bone marrows, but essentially it is a small 300 micrometer spheroid. You have the stromal cells on the back, and you have these stem cells dividing and differentiating into the bloodstream in order to finally produce the necessary blood cell types. This bone marrow worked in different combinations. We had a long history with that, starting in 2016-17 with a bone marrow here at Technische Universität, and you had some presentations on that bone marrow from Rhiannon. For me, the most important part is that this bone marrow is continuously producing lineages, different lineages. And you have learned from other bone marrow models that it's not only erythroid, myeloid, and platelet lineages. You can push it to NK cells. We showed that. Others showed that you can push it to pre-T and pre-B cells, but they are premature. But they are coming up in relevant numbers, so you can introduce that into the thing. And as soon as a team at Charité started to change the ceramic matrix to real bone, which we are deriving from patients and producing for transplants, they even could make long-term metal-specific biomaterial accumulation studies with regard to toxicity of that accumulation. So it is in plastic model. So our take home here was if we now provide intracapillary access into this multi-organ circulation, including a lung, and add donors' white blood cells to establish relevant immunocompetence, you can have a continuous flow of whole blood and can subsidize this whole blood with white blood cells of the same donor taken by an leukapheresis, and that provides a number of possibilities to deal with the diversity of the T cell, with the general diversity of T and B cells at microphysiological system levels. Capillaries, human blood vessel systems. Now with capillaries, the problem is a little bit more important. Keep in mind that the extravasation of white blood cells is in the venular part of our blood system. Here you see the extravasation of white blood cells from a venular part where you have a damage in the skin. You see the white blood cells crawling there. So that is a venular part, not a capillary issue, and not an arterial part issue. And the second part is the most important one. Each physiological organoid has a capillary with an arterial in and a venal out. These capillaries are not longer than 1.5 millimeters, which describes the size, the maximum size of each of those physiological things, and that's why we have so many of them. Yeah? And here is gas exchange, nutrient supply, waste removal, and reabsorption concentrated to 0.5 to 1.5 millimeter of a certain unit. And the diameter of these most capillaries is the diameter of erythrocyte, 8 micrometers. If the erythrocytes are not squashed by the endothelial cells, the transfer of oxygen is much more lower. We started to developed a number of robust processes to vascularize, to endothelialize, to be correct, all our channels and the bottoms of the compartments here. We were able to show this. You can make time-lapse video analysis how these cells, no matter whether you are using primary cells or IPS-derived endothelial cells, how they confer spreading out under pulsatile flow. So that is the first part of the small vessel system, like the larger endothelial vessels. And for the capillaries, we have enough space in our systems to then go smaller with the capillaries in these areas of tissue culture. So we go down with 3D printing technologies into much smaller vessels, and at the end of the day, we are trying to rebuild the capillary self-assembly. We were able to show that this embryonal fact that they are forming by themselves but are not closed in the vasculature could be reproduced. And if you put it into a certain design here, you can then close these vasculatures, and then, as many of you are in the areas of vasculature, you see the sprouting and the readiness to go for angiogenesis into tissues. That are the white blood cells here. This is endothelial cells. So with that, I just give you a little glimpse about how we try to get more and more into that things. Now, keep in mind that we have 28 assays around, and these 28 assays are working with very different combinations of organs. So we are quite sure that this knowledge which we are gaining together with our partners and customers on all these combinations helps us to collect an organismoid, to assemble an organismoid. Later, last topic here was, as you remember, was like how to make a healthy organismoid than a diseased organismoid. And the answer is make it first healthy and then start to apply how Thomas called it eco-exposome. So whatever is not genetically predicted is eco-exposome from my side, so infected, or in case of liver pancreas combinations, hyperglycemia, low glycemia, and we combined it, by the way, together with, or others combined it, AstraZeneca and the Linköping's University combined it with computational modelings, which helps us to reduce the number of chips significantly if you have the model behind it. So you can induce, as soon as you have a human healthy model, you can induce a disease in a human-like way. We have a lot of partnerships currently ongoing, or a defined number of partnerships with different aspects of disease or chemical assessment here. And that is where we're gaining the next idea to put it into the long-term vision. Now, what are the principles of the organismoid theory? We need, first of all, to recapitulate human ontogenesis. And this 20-year human ontogenesis might be difficult to put on the ship. But everything what we are learning about embryonal development and other developments in each of the organs, as long as they are growing and maturing, counts into the artificial ontogenesis. And then we need to have a stable long-term homeostasis of mature organs. For the ontogenesis, it's important to know that the majority of what we are doing with organoids is more or less is comparable to week 3. Some of the things are week 10. The heart is starting to beat at week 3, and the first erythrocyte is running at week 3. So everything which happens before is easy to model in non-oxygenated systems. It becomes more difficult later. But we are confident that we can put that into a certain pre-culture to mature organs, and then put them together in a chip, make a final maturation in the chips, because crosstalk helps to fastly maturate, and then model the disease areas. With regard to timelines, we have different, the theory implements short-term, mid-term, and long-term timelines in order to get access to any of the disease and use these systems in any of the preclinical trials with the relevant timelines. Human organs are built by multiple identical functionally self-reliant structural units. That is one of the principles of the theory. Such physiological organoids, or however we call it, functional units, are evolutionarily conserved and subject to genetically encoded self-assembling, vascular perfusion, a connective tissue bed, and organ-specific stem cell niches are essential features. If you are lacking that, you cannot recreate it. Accelerated terminal differentiation of premature organoids is enabled by in vitro training programs for single organs, and many of you have shown that you can train immune organoids into real immune organs or others, and might be enforced by organismoid-based on-chip crosstalk. So the multi-organ chip guys among you have shown, including Jordana, that when these pre-organoids come into contact and start to work on each other, they are fastly differentiating further. The initiation of disease in healthy organismoids should be based on the natural pathogenesis of that disease. If it is a genetic disease, it is incorporated anyway, but everything else.
Proprietary multi-organ chip
this is now
technology
the final
is a microphysiological
background
system
which we have
capable
here.
of maintaining and culturing miniaturized organs. Let's take a closer look at the human on a chip. The next generation of Tissue's multi-organ chips has the area of a standard glass microscopic slide. It consists of 4 layers: an adapter plate, a nutrition plate, an organ plate, and a sensor plate. A common blood vasculature interconnects the different organ models, such as the intestine, the liver, and the pancreas. Nutrients are absorbed by the intestinal model and then distributed by the circulatory system. Insulin and bile is produced by the pancreas and the liver, respectively. Food which is not absorbed by the intestine is excreted. The kidney model filters metabolic wastes, excess irons, and chemicals from the blood to form urine. Additional organ models on the chip include a lung, bone marrow, skin, adipose tissue, brain and ovaries or testicles. Substances can be applied intravenously by direct injection into the circulation. The transparent sensor plate allows the electrical coupling of organs and direct microscopic access. Substances can also be applied topically onto the skin. Oral uptake and inhalation can be emulated, respectively. The chips can be run fully automated over extended periods of time by employing state-of-the-art robotics. The human on a chip is supposed to be sufficiently flexible for diverse disease modeling and to bear the potential of ultimately replacing animal models for systemic substance testing.
The automates are there, the multi-organ chips are there, but the vision is still a vision. So those who have visited our laboratories over the last 5 days, have seen the automated systems already. They are working with the 4 organ chips in automated fashion, but it still takes time. So that's why I'm saying this might be a dream for many of you. And I want just to summarize now. That first, one question: who now believes that we sometimes in the next decades can come to that point? Please raise your hands. A little bit more. Very good. Summary and outlook, just short. I think that the 138 years of in vitro cell culture have made the largest progress in the middle of the last century, but not for our topic, but for tumor cell lines. But now the last 10 years is the largest progress for primary tissues, and the understanding that at least microfluidics are necessary because blood is flowing has made a lot of progress in microfluidic systems. I'm quite sure that many of you will come up in the next decade with minimal human body on a chip systems, and I'm very happy then to exchange knowledge and see all that. Let's make some statements. It is important to prevent any consciousness and empathy on that chips, and that's why we decided for chips and not for half a kilogram bioreactors, because the empathy and the mind and soul in humans are directly related with the exact architecture of the entire 1.2 kilogram or 1.3 or 1.1 kilogram brain. So I'm happy that we cannot do that, but can partially go into questions with context of use. Hard is difficult at this scale. So everything which is based on scale is difficult to model in the system. But anyhow, I think that these kind of, and then we would call it patient on a chip facilities. If you have like a minimal organism, if this organism is pathophysiologically induced, like the diseases are induced as we have it in humans, like with infection or chemicals for tumor or genetical backgrounds, then we will have patient on a chip facilities, and we think that they can make really a big deal for drug development, personalized medicine, and at a certain scale, and adoption of these technologies also for population-wide precision health. We think that a lot of laboratory animal studies can be replaced, except those which are related to brain and to mind and soul, right? And that will impact drug, like make a paradigm shift in drug development. And we hope that really the researchers among you, the basic researchers, start to take this organismoid models instead of making crazy humanized animal models. So for those of you who became enthusiasts, I have some homework. If you have any idea how to make self-sustained thermoregulation in our chips, or hear, taste, and smell, write me an email. Here's my email, and we can get into a good discussion. With that, I would like to thank our incredible team at the Technische Universität and at TICHIUS, and every of our research partners and customers, many of them here in the room. I thank you very much for your attention.